So the different thermodynamic processes that they want you to know in this, they want you to know isobaric, and that's constant pressure. They want you to know constant volume. And that is also called isochoric. I'm putting their more common names, not in parentheses. So this is a situation where we're keeping pressure constant. This is a situation where we're keeping volume constant. What's the other variable we're talking about manipulating? If we're thinking about the ideal gas equation, the variable that's in there is temperature. So isothermal is what that's called. And that's constant temperature. We also do have to think about a situation where we don't add any heat to the system, because heat's another way you can add energy. And we call that adiabatic. All right, so there's our 4 processes they want us to know. And what I'd like to look at is the change in thermal energy or internal energy. I'd like to look at whether we're adding heat to the system, whether we're adding work to the system, and also how do you do it? What would that look like in the lab? And I'm going to say for all of these, assume we're adding energy. So how could we put energy into a system at constant pressure? We're going to heat something up, but it's to keep it at constant pressure. What should it be like? So what kind of container are we heating? Heat an expandable container. In the case of isobaric, it's hard to figure out the change in thermal energy, heat, or work, because it's possible that we could be adding heat. It's possible that we could be adding work. And how those two combine is going to be difficult. Because on that graph, I was talking about work being done. But work's not the only way energy can go in and out of the system. Heat is too. So for constant pressure processes, we can figure out the work done pretty easily. That's the area on a PV graph. But we also have to think about the heat and the thermal energy. So isobaric is a little bit harder for us to deal with what we've got right now. Let's talk about constant volume. If we have a constant volume process, I'm going to hold that one of these values is 0. Work is 0. So according to our equation, the change in thermal energy is equal to work plus heat. That means the change in thermal energy just has to be equal to the heat we have. Because if work is 0, then those two are equal. I want you guys to look at the equation sheet and see if you can see an equation that might be relevant for isothermal. That we have to look at this other equation. It relates kinetic energy to temperature. That's the equation that I think really is what we use to justify that increasing the temperature of something increases the speed of the molecules. So constant temperature essentially implies that the average speed of the molecules is staying the same. So this is the equation I'm referring to and all that. And it's the average kinetic energy for a single molecule of a gas. Notice it's just entirely dependent on temperature.
If we think about all the molecules of the gas, that starts to get us the internal energy of the system. And notice the only difference is N. N is the number of molecules we're talking about. So internal energy of the system just depends on temperature.
There's no change in the average kinetic energy of a molecule, and there's no overall change in the energy that's stored in the motion of these molecules. That means our change in thermal energy for an isothermal is zero. You can add energy to a system by work or heat. So if you have a system that's having energy transferring, but its overall thermal energy is not changing, if we go back to this equation here, let's say I did heat this system. I put, I don't know, a Bunsen burner under it and started to heat it. What must the work be in that case? It must be negative Q. So in other words, the work and the heat transfer must be the same if you're adding energy to a system, but the internal energy is not changing. So as quickly as we add energy through heat, we must be doing some work to take that energy away. Can anyone think of how you could make a system change energy in the lab without changing its temperature? Okay, so we could change the size of the container. That's definitely one thing. So that's going to be doing work because that's a delta V. So depending on whether we're compressing it or expanding it, we're doing work or work is being done. But based on what we've got here, what has to happen if we're adding work to the system? What has to happen with heat? To have a heat transfer out of the system. And if, on the contrary, if we're taking energy out by doing work, that means we have to put heat into the system. But the temperature can't ever change. So it's got to be a container that can change its size. But there has to be a place where we can add energy from if we need to, or take it away. So in chemistry, do you know what's a great way to make it so that every time you need to add heat energy, it's there, and every time you take it away, it's there? It's a water bath. So if we are expanding a piston or something in a water bath, that's energy leaving the system because work is being done. Where could the energy come in to replace that lost energy? It could come from the water. If we then turn around and compress the piston, we're adding energy to the system via work. That has to leave if we're staying at a constant temperature. Where could it come from? The water. So water bath is the best way to keep something constant temperature. All right, so the last one is adiabatic. Adiabatic, I feel like, is hard to figure out, but the best way to remember it is there's one of these where you don't add any heat. We've seen one where we do no work. That's constant volume. So we need one where we don't add any heat, and that's this one. So in that case, any work we do, if Q is 0, any work we do is just going to be the change in thermal energy. And since this one is hard to picture, I'm going to just tell you, use an insulated container. Or do it so fast that heat doesn't have a time to transfer.